Hi, folks. Welcome to the presentation. I'm David Steele from Arcturus, and I'm joined today by Ali Orrs from NXP Semiconductors and my colleague from Arcturus, Jonathan Rinn. We're on a tight timeline today, so let's jump right in and get started. Our topic today is optimize and scale, squeezing the most out of your edge AI. Building edge AI devices is complex. There are a lot of components with significant interdependencies that need to come together in a resource-constrained system. From the standpoint of a developer, what is critical to understand in advance is where optimizations can be made, how effective they are, and what trade-offs may result. With this knowledge, it's possible to formulate an attack plan. In other words, we can define the areas where we can achieve the biggest bang for our buck. Do we focus on optimizing our ML AI, or do we focus on our application and logic? So this presentation will be broken down into two parts: low-level enablement and optimization, which will be covered by Ali from NXP, and a second part, which will cover application scalability and runtime optimization techniques, which will be covered by myself and Jonathan from Arcturus. So with that, why don't I hand things over to Ali Orrs from NXP to kick things off. Ali?
Great. Thank you, David. At NXP, we're fundamentally a semiconductor vendor, and we cover devices in the microcontroller and applications processor space. And for our silicon devices, we've built an edge intelligence EIQ machine learning software development environment, which provides a collection of development tools, utilities, libraries for building your ML applications using these MCUs and NPUs from NXP's portfolio of devices. The EIQ machine learning software can be leveraged as part of an existing user's flow, or can be used for the complete flow of a supervised machine learning development for a given application target. What we offer in the EIQ machine learning software development environment, this is the full view. The key for NXP is to enable all levels of user experience and user capabilities, from ML experts and data scientists, which are very familiar with ML workloads and solution building, having some of their own tools, some of their own scripts, and a lot of data sets, to embedded developers that are just starting to develop machine learning solutions and are looking at applications, getting more familiar with models, inference engines, and data sets themselves. So we aim to cover the whole wide spectrum of user experience and allow the users, as their learning curve is achieved, to still remain within the same tool flow and leverage it as needed by their end applications. For this, we've put together our EIQ toolkit, which is a ML development experience tool flow tool, provides different flows for bringing in your own data, to work with data within the tool, to do data curation, model selection, model training, optimization, quantization, down to validation and deployment, or to come in with a trained model with bring your own model workflow and actually convert within the tool and deploy onto NXP devices. We also complemented the toolkit with the EIQ portal, which is a graphical user interface, fairly intuitive to use, where you can actually build vision-based ML applications all within the tool, leveraging the GUI itself. And to this mix, we also have our ecosystem partners like Arcturus also coming as part of the EIQ marketplace, where they can offer additional wares to speed your time to market. For the runtime aspect of it, within the EIQ software environment, we offer various EIQ inference engines that we support, both from the open source, open community base, such as TensorFlow Lite, TensorFlow Lite for microcontrollers, specifically for MCUs, ARM-NN, Glow compiler support, or NNX runtime support. And to this, we've also added a proprietary inference engine, which we can offer a more long-term maintained solution with, called DeepViewRT, from our collaboration with Ozone Technologies. And all of these baseline enablements, the EIQ toolkit, the EIQ portal, and EIQ inference options, including DeepViewRT, are all provided as baseline enablement with no additional licensing fees needed. The inference engines for MCUs are available through the MCU Expresso SDK build, and for the MPUs, for the applications processors, available with our Yocto VSP release. The overall coverage that we have in terms of the inference engines to devices, as well as the individual compute engines within these devices, such as the applications processors that have both ARM Cortex-A CPUs, DSPs, GPUs, and NPUs, can be seen in this chart, where we offer various inference engines with different optimizations available in each for these different compute engines. Similarly, in the microcontroller side, we have devices in our crossover iDynamics RT family, where you can select DPU-RT or TensorFlow Lite for micro, or Glow as an inference engine for the different engines in the cores themselves for ARM Cortex-M cores, as well as DSPs in the iDynamics RT600 device family. And to before I pass it back to David to really highlight some of the advantages of when we start adding NPUs, so dedicated machine learning accelerators, to the mix of compute engines available in the SoCs from NXP. What we're showing in this chart is a comparison between a single core CPU core versus an NPU core, so a dedicated machine learning accelerator. And on average, for detection and classification models such as MobileNet V1 and V2, as well as MobileNet V1 with SSD detector added to it, we're seeing that on average you have a 15 to 40x improvement for a quantized model between running it on a CPU core versus a dedicated NPU core. And I think that will segue nicely into what David and Jonathan will be presenting.
So thanks, Ali. So I guess, Ali, what you've shown is the kind of the low-level tools that help enable data optimized models and get everything ready for the edge runtime. What I want to talk about is the importance of the application architecture around that model, and why flexibility and scalability are really critical in achieving the best possible performance. Given that perspective, what we need to do is pull the lens back a little bit and talk about what we need to achieve at the system level. And of course, I'm going to be talking about this from myopically from Arcturus's perspective, which is vision systems, although a lot of this is transferable to other edge AI domains as well. Ultimately, at the system level, we are trying to find the right balance between frames per second and model processing for our application. And there are a number of considerations that will affect this. For example, the NPU or GPU that we are using may be underutilized, and improved parallelism could gain us efficiency in this area. Perhaps our application may benefit from the deeper insights that more than one model running concurrently would provide. There may also be some specific edge runtime or model precision dependencies that require a specific model to be run on a specific piece of hardware for the best efficiency. And finally, there's always a need to support future models and improvements, which may not necessarily have the same performance characteristics or even dependencies. Ultimately, this balancing act requires considerable experimentation, and in turn, that requires an architecture that can easily support various vision pipelines without destabilizing the system or timing. And this is the kind of approach that we use at Arcturus, along with some tooling that allows us to create and deploy these pipelines at runtime on the edge device. It's this flexibility that dramatically accelerates our experimentation and also helps with our scalability and helps future-proof our systems. And we can look at a few pipeline examples to illustrate what can sort of be achieved. Here are 4 different pipeline examples that scale either model processing or streams. The first one is running 2 identical models concurrently, with each model processing an alternate frame from the video stream. Now, what this does is this specifically improves our FPS by increasing the parallelism in our system and making better use of the hardware we have. The second example is running 2 different models concurrently, with each model processing the same frame. And the output of these 2 models is then combined at the application to provide deeper insight about the scene. The third and fourth examples are processing multiple video streams at the same time, and this provides parallelism at the application. What's interesting is the first 2 approaches are particularly interesting because this concurrent model processing can dramatically affect what we can achieve at the edge, either optimizing performance to increase our FPS or providing deeper insights. So with that sort of context, what I'd like to do is hand things over to Jonathan Rinn, who is one of our data scientists at Arcturus. Jonathan is going to expand on these key concepts of scaling and concurrent model processing, and he's going to illustrate some optimization techniques and their net benefits. Jonathan?
Thanks, David. Yeah, so I'm going to take you through some of these optimization techniques that can be used to squeeze the most out of your systems. And basically just trying to answer the question, how do we scale while maximizing throughput and reducing the latency of our real-time system? So first we'll have a look at some scaling techniques such as concurrent processing, batching, tiling, and then I'll briefly touch upon some model optimization techniques. Now, when it comes to the scaling techniques, we're typically looking at the trade-off between throughput and latency of the system, whereas when we look at the model optimizations, you'll start to see a trade-off with accuracy also. So starting with concurrent processing, on the next slide, it simply means that two or more actions are being executed at the same time. So for the purpose of relating this to what we're talking about today, it's going to be the process of executing two or more models at the same time. So these could be two different models, such as object detection and a segmentation model, or it could be executing the same model multiple times. So let's look at the latter and see how concurrent processing might be beneficial when we need to run the same model more than once. So let's say, for instance, we're using an embeddings model, which is typically used to generate appearance vectors for people in a frame. So if you're going to do object tracking or something like that, this model actually needs to be run once for each person. So if we have 100 people in the frame, we're going to need to run this model 100 times. So you can start to see how this begins to create a bottleneck in your overall system. Now, to reduce this bottleneck, we're actually able to create multiple processes to run these networks concurrently while syncing the data afterwards. So if we use MobileNet v1 as an example and say there are 4 people in the frame, we're able to reduce the total processing time down from 120 milliseconds to 60 milliseconds. So of this 60 milliseconds, 30 is going to be your standard inference time with an extra 30 milliseconds from the overhead of the extra processes. So this achieves our original goal of reducing the latency, which then can in return increase the throughput of the node and as a result, a higher FPS of that node and your actual overall system. Now, this being said, concurrent processing might not be the best option for everybody's use case. So with this method comes increased complexity. You're going to have additional memory management and IPC techniques that are needed to sync the data and bring the system back up to a working state. You're going to have increased memory consumption from running a direct copy of your process. And it can be very resource intensive, whether you're running it on CPU, NPU, or GPU. So also depending on the resources of your system and how limited they might be, you can experience varying inference and pre-processing times. So given these resource intensive cons, this method might not be the best option for everybody. So we'll jump right into the next one, which is called batch processing. So this is when items are grouped together to be processed at a later time, usually with little to no user interaction. So to relate this to what we're talking about today, it's going to be the process of grouping images together and running inference on them with a single execution command. And this is often referred to as runtime batch inference. So if you have a model, say with a batch size of n, you're able to collect and store n images, load them into a single input tensor, and feed them into the network with a command, receiving a single output tensor. So if we have a look at this graph, you can see that there's an increased throughput, and there's also an increased latency. So even though the models are still running sequentially when batching, and we don't typically see a performance increase with the inference time itself, where we do see a performance increase is in the pre-processing time, since we're only loading one input tensor, regardless of the batch size or the number of frames being processed. Now we do see that increased latency, which can be expected when doing most methods of batching, given you're processing more data at a single point in time. But depending on your use case, this can actually be very beneficial. So if we refer back to the previous example of running an embeddings model n number of times on a frame, the latency of that embeddings node is actually reduced. And the reason for this is because we have the input images, which are going to be those cropped images of people in the frame, readily available to feed through the network in a batch. So if you take a step back and look at the bigger picture, the latency of that embeddings node is actually reduced. So while batching is a lot less complex than concurrent processing and definitely can simplify your system, like every optimization technique, it does have its drawbacks. So depending on the size of your batch, where or how you're loading it into memory, you will typically see an increase in RAM consumption. Another drawback is the model and backend compatibility. So does your model support batch size greater than 1? Does the backend, such as TF Lite or ArmNN, even support a dynamic or fixed batch size? These are all things that are going to need to be considered when trying to implement runtime batch inference. And of course, we have the increased latency talked about before, which can help or hinder your system depending on what you're using batch processing for. So when we compare these two methods, batching is typically an ideal technique when you have limited resources or when you have a large number of inputs, whereas concurrent processing might be a better route to go if your inputs are reduced or your resource consumption isn't as big as a concern. Or you could always use a hybrid method of the two that best suits your system. Another situation where you might find batching useful is a technique called tiling, which I actually find extremely interesting. So this is used to increase the accuracy of your model or boost the accuracy of your model. So in a real-time system, you may not always be able to use the most accurate model. So you might have to choose a lighter weight model just to achieve any performance or throughput requirements in your system. So as a result, when you use these lighter weight models, the accuracy is typically lower. But what you can actually do is take your original image and split it into subsequent tiles and feed them individually or as a batch through your network. As a result, the model is now able to detect objects that it could not before. So with a model like MobileNet v2 that typically struggles with detecting smaller objects, it's now able to detect these objects within the tiled frames. So if we have a look at this slide, the images on the top are the frames with the initial detections without tiling, and the images on the bottom are the detections with tiling. So you can obviously see a clear improvement in the number of detections that are there. Now, if you look a little bit closer, you're actually going to see that there was an increase in the number of false positives, which can be a downside to tiling. Along with the false positives comes the added overhead of the pre and post processing. So you're going to have to stitch back together these detections and the frames, and you're going to have an increased latency since you now have to run the model X number of times, depending on how many tiles you split your image into. So why don't we jump on over into some model optimization techniques. These are also used to increase the throughput and reduce the latency. However, it usually comes at the cost of your model accuracy. So we have model input size, which is simply reducing the input size of your model. We have model depth reduction, which is reducing the number of channels at each layer of your network. And we have network quantization, which is reducing the precision. So it could be from floating point 32 to floating point 16, or all the way down to int 8. So if we have a look at reducing the model input size first, we can see that as the input size is reduced, the throughput increases with a slight hit to the accuracy. So where this would be beneficial in a system is where the accuracy may not be as important as the throughput, and you can afford to lose a little bit of that top one accuracy, maybe 1 to 2, maybe 3%. And similarly, we'll have a look at the model depth reduction now. So as previously stated, this is just reducing the number of channels per layer. So if you have a depth multiplier of 0.75, you now have 75% of the original channels within that layer. So with model depth reduction, we see a very similar trend to the model input size reduction, which is the throughput increases quite a bit, actually, at the expense of losing a little bit of your accuracy. So you may not want to reduce the model down to 25% of your original model and take that 20% accuracy hit, but you very well could reduce it to 75% and only see a 3% accuracy hit, but almost double your throughput. So this really just depends on what your objectives are and the overall goal of your system. And finally, we have what I like to call the holy grail of optimizations, which is model quantization. So with the smallest hit to model accuracy and the greatest improvements to throughput, this is a technique that's commonly used in real-time systems and embedded systems. So if we have a look at MobileNet v1, we only see a 1% decrease in accuracy and nearly double the throughput. So this is definitely a technique to keep in mind when you're trying to maximize your throughput and reduce your latency. And to top it all off and just wrap things up, who says that you're only allowed to use one of these model optimization techniques? You can combine all three, you can interchange them. It's really just to find a sweet spot between your throughput and your accuracy that's right for you and the system that you're trying to develop. So if we look at this chart, at the furthest point left, we have the highest throughput and the lowest accuracy, which is a quantized model with the greatest depth and input size reduction. Whereas at the furthest point right, with the highest accuracy and the lowest throughput, we have a quantized model with the original depth and input size. So hopefully this has shed a little bit of light on some of the beneficial scaling and optimization methods that we use here at Arcturus, and some that are available to you and allow you to pick and choose from these techniques to build and scale a system that's suitable to your needs and requirements. And I think with that being said, I will hand it back to you, David.
Great. Thanks, Jonathan. That is extremely insightful data. Absolutely. So I guess just to wrap things up in the limited time we have, we've pulled together this slide for additional information and links. Ali, do you want to highlight some of the points here from NXP, or do you have anything you wanted to add?
Definitely. Thanks, David. So from NXP, as we mentioned, we have the EIQ machine learning software development environment available from nxp.com/EIQ. We also have ML AI Training Academy with over 20 modules in terms of deploying on MCUs or deploying on applications processors, walkthroughs, and extensive training of how to use the EIQ toolkit itself. And as well, always reachable through our community links for any additional help that our users might need for both the applications processors and the MCUs and the SDK and BSP options for those. Excellent.
And I would just like to add that there are links back to our Brink Edge AI and Vision Analytics product at Arcturus, additional webinar content, papers and articles. And of course, feel free to reach out to us. We're always available to chat, and we'd love to help you develop your Edge AI and ML application. So on behalf of Ali at NXP and Jonathan and myself from Arcturus, we want to thank you for joining us today.